So in this case, if you're looking at 300-pound class ANSI flanges, piping that's rated to 720 psi, we're dealing with a system that meets the ANSI requirement and the pressure rating of the pipe, or far exceeds that. So if you look at just the risk assessment in your project and how to mitigate that problem, it's putting in the surge vessel and giving energy would be a huge plus in protecting our piping system. And again, this is the worst case scenario. The ways of minimizing this transient wave is that, yes, indeed, you could also add in variable speed drives, gradually ramping down the VFD. And in the computer modeling software, we can put that step in there, or you can also put in pump control valves or electromotor operated valves with a controlled shutdown speed, whether you'd leave the pump running or ramp the pump down and slowly close the valve off at a period of time as you gradually come to zero velocity. So at that point, we could get this line even smoother. But again, this is the baseline of looking at the worst case scenario and solving the problem. And again, before we were going to a vacuum condition, you see now the lowest pressure is 40 psi. And again, I'll click here. It's a huge difference because before we were dropping to a full vacuum. So now our pressure differential is 150 psi to 40 psi, back up to 150 psi, putting very minimal stress on the piping system. Now if you look in our model, we have other devices in here. This would be a air vacuum valve. And again, this would allow air to enter into the piping system at this point. If you look into our model, you'll see that at this point, even with the surge vessel, we're dropping below atmospheric pressure. And at this point, that air vacuum valve is allowing air into the piping system to try to keep the line at atmospheric pressure. And again, even with the air vacuum valve on there, you can see the difference in the pressure spike. Again, low operating pressure, but we're trying to minimize the vacuum condition. In the modeling data, again, different components, because as we're looking at sizing a surge vessel in the system, we're going to add other devices, okay? So we have our dampener, but we're going to look at that air vacuum valve. We're going to look at the different pumps, VFDs, and then the control valves in the system, the way we can manipulate the whole entire system to protect the overall integrity. So to give you an example, I clicked on that air valve, and then it's just a standard air vacuum valve, 4-inch diameter with a 0.1 delay. Again, this is some of the research that we've done in modifications that was done to the software since 2006. It was found out that we've created a model, put in all the critical surge components into the system, tested the system, and we found that we were still having surge issues. So the flaw is that the software was assuming that the air vacuum valve would open up instantaneously and break a vacuum in the system. And nobody had ever done any testing, so we took our high-speed computer, started putting it on various different air vacuum valves to find how fast they would open. Now, typically, my default would be 1 second. In this case, I had put 0.1, again, just to show an example. You got to understand we're dealing with a wave speed that's traveling 3,000, in this case, 600 feet per second. So 1 second is an infinite amount of time when we're doing a surge analysis. So there's your before and after. Again, just making the change and modification to your vacuum valve. Was it going to open in a 1/10 of a second or 1 second? You can see if it took a second to open up, which is a 4-inch valve, which means the water had to leave the air vacuum valve. You had to open up a 4-inch seal for it to drop down and let atmospheric air to fall in behind. If there was a delay of 1 second, we're dropping to a full vacuum in our piping system, which in turn created a larger upsurge in the system when that imploded in on itself. So we look at the overall conditions of our system, and all those components. So as you're making a recommendation, your customer says, you know, I may or may not have a problem. It's doing a surge analysis in the system when they're designing a brand new system. When it comes to you already have a system, usually half of our business is new design. Next half is I already have my piping system and we're having problems. Well, what they're not telling you is their problems are they're literally tearing apart their piping system. They've repaired the piping system and they want you to solve the problem. So if it's there and in operation, that's where we go in with our transient monitoring computer, put it on the line, and then we can analyze the shock waves that are happening in the system. I've got some great examples of that. Let's see. Here's an example of a 2-pump trip. We're operating at 186 psi. We've done 1 pump trip, then we're doing 2 pump trip, and looking at proving our surge analysis and looking at the worst case scenario. Now again, if we go back to some of the books that were written 14 years ago, there was one grad student who wrote his PhD on this shock wave right here. Anybody have an idea what that would be in the surge analysis? It starts off, it looks like we're running fine, we're in steady state, and I can't even tell if I'm having an upsurge or a downsurge. So this was the dilemma before we had high-speed computers and computer surge systems that could read pressure waves and capture that data. So from that pressure wave and with this transient monitoring equipment, we can expand it out to this. Whereas we are running our pump 186 psi, we turn off the pump. We have inertia of the pump as the negative wave oscillates out, and then that wave oscillates back towards the pump. And here we can see how fast we have reversal of flow. And at this point right here is when our check valve closes. From this step point to this step point is when that check valve closed. And when the check valve closed, it created that upsurge that went up to, in this case, 255 psi. If we look at the computer surge analysis in the simulation in the check valve's manufacturer, they said their check valve would close in a certain time step. When we first did this test, we exceeded the pressure rating of the pipe. Okay, went back to the manufacturer and said, you said your check valve would close like this, so they added different spring packs to their check valve to get it closed faster and faster until we got to this data. But again, we're able to record at a rate where it was just a shock wave, or if you had a regular pressure transmitter or a liquid filled gauge in your system, you might have never even seen any of the shock wave occurring. Here's another example of an offshore water flood project where we have a charge pump that's pumping at, 350 psi, that's going to a 25,000 horsepower turbine pump, which then we're pumping 18,000 feet into the earth in a water flood project. And what was happening is they were ripping the flanges off of the pump and in the piping system. We had done a surge analysis and we could never get the worst case scenario that would be creating that much damage in the system. So that's where we had a working system. We put in our transient monitoring computer, and this is what we were able to capture, was this is the worst case scenario in the shock wave. So that now we have the real life data, we can then implement this back into the surge analysis and come up with a solution. So we were able to take the model and create almost an identical shock wave in the system. Once we had that, we were able to put in the surge vessel, which in this case was putting in a 200-gallon surge vessel to accept energy. As you see, we're accepting energy because we have an upsurge, and then it gave energy to the downsurge, which our results in our real-life data is now the red line, where we're no longer overpressurizing our system. So that's where surge analysis and the devices make it a lot of fun, where you can improve the system and correct the problem. To go from an extreme standpoint, a pulsation dampener, Blake's smallest dampener is you could get a surge vessel that's 45,000 gallons. So it just depends on the surge analysis, the flow, and the most important thing to remember when you're looking at surge analysis is typically the lower the pressure, the bigger the vessel. And then the higher the pressure, the smaller the vessel. In this case, this is a huge vessel, but we're operating at 70 psi, high flow. We needed to give a lot of energy to that pump trip in the system. This is an example of a surge vessel that is put in a line. This is in Dallas, Texas, and this is a system where they're taking the reuse water from a sewage treatment plant and using it for reuse water for golf courses and the zoo and different customers where they can resell the reuse water from the sewage treatment plant. We started off with 2 customers, the city of Dallas, and we look at that system growing. So we had to start somewhere in our surge analysis and sizing the vessel, and to make sure that we're giving energy based on the amount of pumps that we have. In this case, we have the surge vessel, but we also have a transient monitoring computer that is permanently attached to the pump station. What this does is it's constantly monitoring the liquid level in the surge vessel, that we're recording pump trips and how much energy we're giving to that change in velocity. And we're also recording transients. So I can put this system out in the field, come back a year later, and look at the whole year's data. And when there's a transient event, we can see it going from blue to red in the transient monitoring software. So that's where I can click on that exact day, expand the data, and make sure that the surge vessel gave energy to that change in velocity in the system. Because this is in a sewage treatment plant, we have something what I call is an oh shit alarm, which means a transient event actually occurred, and then it'll notify the operators that they had a pump trip or they had a unforeseen event occur. So when it goes into transient mode, meaning that's recording 100 times a second, it can send off an alarm. It's also critical of the pre-charge pressure in a bladder vessel, which is the same with the dampeners, that if you don't have the pre-charge pressure set right, or for some reason you lost your pre-charge pressure, we're not giving and receiving energy properly. When we look at the surge model, we can look at the gas expansion as we have that change in velocity or accepting that velocity. And we have a given pressure envelope or volume envelope inside the vessel. If for some reason we go outside of that envelope, we have a differential pressure transmitter on the tank, as you see right here. That in cases it's a Rosemont 3051S, which is recording the liquid level in the tank. That information is fed by a 4 to 20 milliamp signal into a 3490 controller. This controller is looking at the high level, low level alarms, and also transmitting that data back to a control room. So we can also, again, see how we're giving and receiving energy, and if for some reason the liquid level increased, which would mean we're losing our pre-charge pressure, that it would also set off an alarm. Something to take into consideration in your computer analysis and that gas expansion is the outside temperature. So we tend to develop a min-max temperature curve for between summer and winter, and in some cases you would have to change your pre-charge pressure. To easily do that, again, this is a 10,000 gallon tank. We have a connection here. We can hook up a compressor or a nitrogen tank to recharge this vessel. Again, another example, this is a raw sewage pump station. operating at about 150 psi. And you can see in the background is our transient monitoring computer, always monitoring this pump station from a transient event. And again, in this case, this is a different type of surge vessel instead of a bladder vessel. This is called a dipping tube surge vessel, which is functioning very similar to a hydrodynamic tank and an air valve in one device, where we have an atmospheric pre-charge charging the vessel, and we have a tube inside the vessel that we allow atmospheric pre-charge to then be compressed as the fluid comes up the dipping tube and a float on top of the vessel that closes off and locks in that energy, so that if we have a pump trip, we have the stored atmospheric energy to give energy to the change in velocity in our system. Because of the gas expansion and that temperature is an issue, in some cases we'll heat trace the vessel itself. And again, here's a monitoring system to make sure we're giving and receiving energy properly. You might think to yourself that that's a huge expense, but tying it into a SCADA system, we can actually take that data and look at our pumping data. Because again, it's recording every time the pumps turn off. We can look at the running average of our pressure. If we're having a pump wear and impeller wear, that's going to be picked up with this transient monitoring data, the pressure data itself. So it's a valuable telltale sign of the overall health of the system. It'll also give us an indication, as we saw in the surge analysis in the model, how an air vacuum valve comes into play in our system, and that if that valve isn't functioning properly, that we'll also pick that up in the transient monitoring data. We spoke a little bit about check valves in the system and how critical a check valve is for the overall health of our piping system. We also mentioned that in a surge vessel that we're giving energy to the change in velocity in the system. We're also sending energy back to the check valve, which is going to close the check valve. In this case, the customer had misapplied the check valve. When they started up the pump, there was no load on the system, which allowed the pump to run off the right-hand side of the pump curve and surge open. Of course, this is a submersible pump, and with the pump running off its curve like that, it sends a startup surge into the system. Now, usually, a startup surge is not as bad as a shutdown change in velocity. This can change when we have a vertical turbine pump and a static water level where the pump turns on, we're compressing the air in the well column, it's coming out through an air release valve, say similar to this air release valve here. The air comes out of the piping system, then we're flowing water, and we're pumping water into the system. The issue in this case is that when we're running our pump and we're looking at the pump operating on the curve, there's no load. So what happens is the pump is running way off the curve on the right-hand side, okay? And then all of a sudden we encounter a flow condition. So we're operating way over on the right-hand side of the pump, spinning much faster than design, and then slam coming over to the left-hand side of the curve. We've recorded transients that where the pump on its curve is normally operating at 90 psi. We have startup pressure surges that exceeded 550 psi, which is detrimental. In this case, it was in a potable water system. So it's, again, you've got to understand all the characteristics of your system to create a solution. So in this case, the design engineer wanted the belt and suspenders, whereas the pumps are variable speed drives. You have check valves, but you also have pump control valves to manipulate the starting and stopping of the pump and the change in velocity. And then if you have a power failure, you have a surge vessel to give energy to that system. All of these components are put into the model to give protection under a worst case scenario and minimize day-to-day transients from occurring. Likewise, in this case, We're pumping 27 miles, 24-inch piping system, 225 psi. The pumps will run off the curve on startup. We take that energy, go through a control valve that is normally open. This is a check valve that is normally closed. When we turn on the pump, this valve is open, so the initial air in startup surge goes through this valve. Then your pump control valve gradually opens up and allows flow into the system. Then when we go to turn off the pump, we slowly close the check valve, slowly open up the relief valve, in a balancing act to minimize the transient from occurring. Again, just part of solutions in the system. Likewise, in this case, booster pumps, pump control valves, and a surge vessel to give energy to the transient wave. In this case, you can also look at it from a pump cycle control, whereas the surge vessel is also minimizing your starts per hour. We have a software package, which is pump cycle control, where you put in the pump curve data, your minimum maximum pressure, your minimum maximum demand, and it'll tell you basically what size surge vessel you need to minimize your system to have less than 6 starts per hour, and it also tells you what your pre-charge pressure needs to be. So we've been talking a little bit about pump trips. One of my favorites is valve closures. So here's an example where we're pumping diesel to a dock. We have a surge vessel here. I'm going to turn that off for the model. This is the valve. This is the culprit right here. We can go up here and look at our change data. This is a 16-inch line. We're filling up a huge tanker in the river with diesel. 16-inch line. And the worst case scenario is our ship is docked here and it breaks away from that dock. We don't want to be dumping, 20,000 gallons of diesel into the river. People will get a little upset. So we close the valve, and we're closing that valve in 2.5 seconds, okay? So when we're flowing and we close this valve in 2.5 seconds, we have an upsurge that occurs. We've got all the components, the piping in the model. Let's take a look at what happens when this occurs. You see the initial big upsurge. Well, we went off the chart. So we're dealing with Schedule 40, 150-pound ANSI rating, which gives us a maximum operating pressure, 285 psi. On the dock itself, very low operating pressure. It's like 30 psi normally when we're filling the ship. When that valve closed in 2.5 seconds, we have an upsurge that went up to 470 psi, which again would be devastating to our piping system when that valve closed. That wave then oscillated back down into a vacuum condition. So it's not a very good scenario there. So we go in. We have a relief valve in this line. And you see the relief valve, per their design, is set to open up at 175 psi and close at 150 psi. This was the criteria that the customer wanted based on their pump curves. The interesting point about their pump curve is that when we're looking at it in steady state condition, our pressure is averages 163 psi. When we're running, you see it's less than 100. Okay, that gave us the average. In the model, we're operating at more than 90 psi. So the question is, why do you set the relief valve at 175 when you know this is, again, our worst case scenario, this is our maximum pressure? So our recommendation is to make a change, not only because we're trying to size the surge vessel. I think that was a Freudian slip, sell. it's to minimize the size of the surge vessel and looking at the overall health of the system. So in our recommendation, it was to change the setting of the safety relief valve to like 104 psi. So again, we can go back into the model, put in the solution. The first solution, of course, would be to put in the dampener to accept energy to that change in velocity in the system. So we're going to go over here and put this vessel in service. 636 cubic feet. Pre-charge pressure is only 2 psi, very low pre-charge pressure. So this is where we are with our solution. And again, we're operating with a system that should not exceed 285 psi. So here's my bench line. With that solution, the pressure goes a little bit over 150 psi, whereas before, without the surge vessel, we were hitting 470 psi. So we can look at the cause and effect and minimize the problem there. So you see, when that wave comes out, we close the valve, we accepted energy, but again, that wave is traveling 3,280 feet per second through our piping system. And that wave is oscillating back to my pump. And if we look at, and this is why it's so critical to have your pump curve data, because at this point, we're driving our pump to deadhead, okay? Then it's going to oscillate back in a negative wave. So again, with that safety relief valve, let's go back into the model and make some modifications to that particular valve. So here's our safety relief valve. It was 175. Let me go back up here. It was 175 and I changed it to 105. And then it was closing at 150. I made it 95. Again, the opening set point you're getting from the manufacturer, through further testing, you could refine your model to see, okay, what did it close off at? Again, it's closing off, and this is a long run of pipe, so we had that negative wave oscillating out. And I put that set point in just by remembering what the negative wave looked like. So, did it on the fly. Let's see what it looks like. So here's the comparison between the two. Again, minimizing the stress in the system, looking at our overall steady state condition at 90-something psi. It's also beneficial in minimizing the set point of that relief valve. So you can see how you're interested in the surge vessel, but how you can work with your client and the engineer with a multiple solution to their problem to, again, refine it. And it's also, this surge vessel, 1,000 gallons is out on the dock. The smaller footprint that we can put out there, again, the overall cost of the project is going to come down. And again, with a 8-inch butterfly valve in this case, that we're closing in 2 seconds, and we're going to look at the cause and effect on our whole entire piping system. Again, this is from BHR's 2000 presentation on surge analysis, pressure surges. Again, remote control pneumatic actuator, close the valve in 2 seconds. We're going to look at the cause and effect in our piping system. And again, we close the valve, all right? Our flow is in this direction. So if we have a pressure gauge here, we look at the pressure here, we're going to see an upsurge, and then it's going to oscillate back as a downsurge. From this point, we have a change in velocity where the velocity is dropping off, so we'll have a downsurge. That wave is going to travel down the piping system until it oscillates back. To this point, we've been talking about straight runs of pipe, okay? So what do you think happens to the shock wave when it hits a 90? Okay? Well, that's where we're going to split the wave. And that's why those input data are critical in the model. And whereas when we started off this presentation with my straight run piece of paper, that's a straight run of pipe. When we look at different nodes in a 90, well, we're splitting that wave. So part of that wave is going to oscillate back, other part of that wave is going to continue down. And when these waves intercede with one another, we're going to again have a huge events occur, which this video is great in depicting that. So I'm going to close the valve. Negative weight goes out, high pressure weight comes back, hits the valve. So again, to solve that problem, close the valve slower or put in a dampener to either give or accept energy. This is the application where you sell two surge vessels, one upstream, one downstream, just like your pulsation and dampener on the pump. So in this case, we're taking that same shock wave and we're sending it into a 90. Why do we have a big, reinforced concrete base, piping reinforcement? Because we're splitting the energy at that wave. You'll see the initial splitting of the wave, and yeah, it's bad, but it's not that bad. But wait till the wave that we split, continue going down the line, oscillates back, and look at the cause and effect on this fitting.
Stationäre Geschwindigkeit, 4 Meter pro Sekunde, ohne Bremsanlage, ohne Rückschlagklappe.
So instead of just 190, we're going to look at the cause and effect across two 90s and how the wave's going to oscillate back and forth. So as we zoom in on this, I have a great story to tell. As you'll see, our piping is very well restrained. So here's a big pipe restraint to keep the pipe from moving, okay? 2 years ago, I went to a pump station, sewage lift station in Canada, where we had 4 pumps. Inside pump station, piping came out, made a 90, ran along the wall, made a 90, came out, surge vessel, and then out into the system. So go in the room, and first thing I say is, I thought we were going to do startup today. And like, yeah, we're going to start up today. I'm like, you have no pipe restraints in your system. And the engineer says, yes, we have pipe restraints. They're right there. I'm like, those are pipe supports. They're not going to restrain the pipe from moving. And he asked me, he's like, who are you? And I'm like, I'm here to start up the surge vessel, but it's over here. All this pipe is going to move through that wall right there when you turn off the pumps. Ah, American, you don't know what you're talking about. So they start up the system, pressurize the system, all is well. And they're like, okay, we're going to turn off the pumps. I'm like, wait one moment. Take a walk outside, look around the building. I'm like, okay, go ahead, turn it off. Turned off the pumps. Piping went right through the wall. They're like, all right, we'll see y'all later. Call me back once you restrain your piping system. So let's look at the cause and effect in this piping system with that change in velocity. So most of the chemical plants I go into, they're like, hey, wait a minute, how'd you get the picture or the video of our piping system moving like that? And I'm like, that's not your piping. They're like, yeah, it is. I just saw our truck go by. And like, oh. Importing a map or a picture onto the model helps your customer understand their system. Again, we have a refinery. I'm like, draw it out. They give you 50 pages of all the piping in the system. And I'm like, give me an aerial picture, a Google picture, that we can look down so that when the operators are looking at our surge analysis, they get a feel for what's going on in their system. So I just overlaid a map, and this is what we built the surge analysis on. Again, we have multiple pumps in series. We're pumping several miles. In this case, we're pumping jet fuel to an airport. The issue at the airport is there is a control valve right here that can close. When the tank is full, the valve closes. The input data and the closing time of the valve, we're running the model for 5 seconds in steady state condition, and then we're going to close the valve. We're going to close the valve in 14 seconds. And we'll look at the cause and effect on this valve closing. The CV of the valve is 3,600 gallons per minute with 1 psi pressure drop, and we're closing this valve linearly over that time step. And we're going to look at the cause and effect. This particular valve is isolating the low pressure piping system from the high pressure piping system. On the upstream side of the system, the piping is a heavier wall design, can handle the larger pressure envelope. Coming into this facility, it's 150-pound ANSI rated pipe. That's our maximum cutoff is, again, 285 psi. You could go throughout this whole entire system and put in higher pressure rating pipe, and this was part of our recommendation, but the cost was 100-fold of putting in a surge vessel and controlling this particular valve. So let's look at the cause and effect in the system when this tank is full and that valve closes. We're operating inside our facility at 50 psi. That valve closed and we locked in a pressure of 750 psi, which is twice the pressure rating of our piping system, which means all that locked in there, dangerous scenario. If you didn't break something, a lot of stored energy in there. So not a good scenario. So you see the upsurge, the vessel accepts that energy and then that valve closed. So you can see how critical that valve also closing as we built this model is. So I personally didn't trust the valve closing like that and wanted to see for myself that the valve would close and everything went fine prior to putting all this equipment out in the field. So I've got a great video showing that valve closing and some of the testing that we did with that valve. And again, our objective is to keep the pressure it's supposed to be below 285 psi. As I said, you get a little over 300 psi spike there. Would have to work on the pre-charge pressure in that valve and the step point of when that valve is going to function. So you see here, the event occurred and we have an upsurge taking place. So at 20 seconds, between 20 seconds, it looks like 35 seconds, I had this window of opportunity to close this valve, okay? You can see I've got time to play with on that upsurge. I know where my normal operating pressure is. So in this case, when I see, maybe it's 100 psi, I'm going to close that valve. I look at normal operating data. This is where, again, you can model your system. You can put the surge vessel in there. You can put that pre-charge. But it's so critical of testing the system in the field and calibrating the system in the field and making adjustments. In this case, we have that control valve that's locking the whole system in on that upsurge. So I have a transmitter there that when I reach a set point, it fires my valve closed. So we have that field adjustment. We can also, again, as I said, look at the vessel itself. So we've gotten our pressure down to 240 psi, whereas here's the change I made, and that is all on the trigger that's closing that one valve when we have an upsurge. So you can see how critical it is in doing a field adjustment proof of design. In this case, we had a system that exceeded our pressure rating of the pipe, making a small modification to the trigger of that valve. We were able to come within our pressure envelope. So let's take a look at that valve, because we started this off thinking, I've got the perfect model, the perfect solution. Can I get the valve to actually do that?
Just a little bit of a delay there, but hell, that's going open, so that shouldn't really matter, right? We're concerned about closing in 1 second. So that took us to just over 100 psi.
Okay.
So that's 2 operations. We lost, say, 40 pounds. You want to watch the ball snap or photo it? Now that you're sure you're not going to get hit with something, or reasonably sure? Okay, 3, 2, 1.
Wow.
So now that I know I have, I need 2 seconds, I can adjust the transmitter to react, and valve closed, and all worked per design.